I'm Dr. K. Raghu Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering. The course name is Unconventional Machining Process. Here today's topic is Electrodischarge Machining and Workpiece Material Removal. Right. These three are the course learning outcomes. At the end of the session, student will be able to understand the fundamentals of electrodischarge machining. Second one, explain the evolution and applications of electrodischarge machining. Third one, understand the wear of workpiece material and the factors influence to it. Okay, these three are the course learning outcomes of the today's topic. Right. So non-traditional machining process. Okay. So under non-traditional machining process, we have three broad categories: mechanical, thermal, chemical and electrochemical. So under mechanical, we have covered ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. So under thermal category, electrodischarge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Under chemical and electrochemical machining, chemical milling, plasma chemical milling, electrochemical milling. However, today we are learning electrodischarge machining and its workpiece removal. Workpiece material removal. Okay, right. Now let us discuss briefly the history of idiom. Okay, see here, the electrodischarge machining began during the World Wars I and II. Okay, the history of electrodischarge machining dates back to the days of World War I and II, when B.R. and N.I. Lazarenko invented the relaxation circuit RC. Okay, now this relaxation circuit RC is an important parameter for the electrodischarge machining mechanism. Okay, what is RC? Relaxation circuit. Relaxation circuit. Okay, right. Now, here for this electrodischarge machining, we are using servo control mechanism in order to maintain the gap between the tool and the workpiece. Okay, so this is tool, this is workpiece. Okay, this is gap. Okay, so here an arc will produce between the electrode and workpiece. So here the negative electrode is said to be tool and the positive electrode is said to be workpiece. In other words, this is cathode, negative electrode, and this is anode, positive electrode. Okay, right. Now we briefly look at the evolution of electrodischarge machine. So during 1940s, die sinking by electrodischarge machining has been refined using pulse generators, planetary and orbital motion techniques, computer numerical control techniques, adaptive control systems. Okay, now let me repeat: pulse generators, planetary and orbital motion techniques. Third one, computer numerical control. Fourth one, adaptive control systems. Right. During 1960s, the extensive research led the progress of electrical discharge machining when numerous problems related to mathematical modeling were tackled. See here, in order to machine a regular shapes like cylindrical hole on a or in a prismatic bar. Okay, let us say we have hole from this face. We can make by using drilling machine. Okay, suppose if we want to cut a complex contour shape with varying x, y, and z directions, then we have to go with mathematical modeling with complex geometry tools like Bezier surfaces and B-spline surfaces using splines concept. Okay, right. So that is about the mathematical modeling or the electro discharge machining of complex shapes machining. Right. Next one is evolution of wire EDM. The evolution of wire EDM in the 1970s was due to the powerful generators, new wire tool electrodes, improved machine intelligence, and better flashing. Okay. However, we will see this wire EDM in the subsequent lectures. Recently, the machining speed has gone up by 20 times, which has decreased machining costs by at least 30% and improved the surface finish by a factor 15. See how development towards the machining process. Right. Next, advantages of electro discharge machining. Okay, so these are the four important advantages of electrical discharge machining. First one, cavities with thin wall and fine features can be produced. See, usually when the wall thickness is very less, it is very difficult to make small features like holes or slots. Okay, but with the electro discharge machining, it is possible. Second one, difficult geometry is possible. Already we have discussed that complex geometry like Bezier surfaces or B-spline surfaces can be machined by using this electro discharge machine. Right. Third one, the use of EDM is not affected by the hardness of the work material. So whatever it may be the workpiece hardness or brittleness, we can easily machine by using electrical discharge machine. Last one is the process is burr free. Okay, there will not be burr at the end of the machining process. Okay, right. During the machining, both electrode and the workpiece are immersed in dielectric fluid medium. Okay, so constantly the dielectric fluid medium is fed and circulate between the tool and workpiece so that during the machining all the burrs will flush away from the tool and workpiece. Right. Mechanism of material removal. This is the main content in the today's topic. Okay, right. EDM, electro discharge machining. So electro discharge machining phase and plasma phase. Here, this is the tool or negative electrode. This is workpiece, positive electrode, and this is the dielectric fluid medium. And here the arc generates between the tool and the workpiece. Right. So from this figure 2, in EDM, the removal of material is based upon the electro-discharge erosion (EDE) effect of electric sparks occurring between two electrodes that are separated by a dielectric liquid. Okay, so this is cathode, negative electrode. Okay, this is anode, positive electrode. Okay, so this is dielectric fluid. Okay, and here the arc generates between tool and the workpiece. So that arc hits the workpiece so that the material removal will take place. Okay, now let us see the heat affected zone of this workpiece and the other things in the subsequent slides. Okay, metal removal takes place as a result of generation of extremely high temperatures generated by the high intensity discharges that melt and evaporate the two electrodes. Okay, so here workpiece and the tool. Okay, tool and workpiece. These two electrodes have a gap and the spark generates so that high temperature will develop and subsequently the material removal takes place. Right. Now let us see pulse current for controlled pulse generator. Okay. Right. A series of voltage pulses from this figure of magnitude about 20 to 120 volts and frequency on the order of 5 kHz is applied between the two electrodes, that is tool and the workpiece, which are separated by a small gap, typically 0.01 to 0.5 mm. Okay, so the gap between the tool and the workpiece is between 0.01 to 0.5 mm. Okay, and the voltage varies between 20 to 120 volts and the frequency the order of 5 kHz. Okay, So these are the important parameters. Now let us see here. The y-axis represents current, the x-axis represents time. Okay, so here on time, off time. Okay, so this is on time, this is off time. Okay, so on off. Okay, this is peak current. Okay, so this is average current. Okay, so however, one cycle represents starting point of on time of one peak to the another peak. Okay, so this is the starting point of on time of one peak, and this is the adjacent starting point of the on time. Okay, okay, here these two are the on time peaks, and this is starting point of the first one, and this is the starting point of the subsequent on time peak. Okay, so the gap between these two is called one cycle, right? Now let us see the mechanism of voltage. Okay, right, when using RC generators, RC means already we have discussed that, relaxation circuit generators, the voltage pulses shown in figure 4 are responsible for material removal. Okay, so here the material removal is due to the relaxation circuit generators. Okay, right, see here the voltage on y-axis and the time on x-axis. Okay, right, here we have to focus on charging time and discharging time. Here the charging time is more than the discharging time. Okay, right, so here from here to here is the charging time. Okay, and it discharges before the subsequent peak. Okay, so this is about discharge voltage. Here one cycle is the gap between the starting and ending of the one peak. Okay, right, now let us see voltage and waveforms during electrical discharge machining. Okay, right, according to Mech of 1988, the application of voltage pulses as shown in figure 5 causes electrical breakdown to the dielectric in a channel of radius 10 microns. Okay, now let us combinedly see the voltage and current in the y-axis and the time in x-axis for both the voltage and current peaks. Okay, so here peak current, this is average current. Okay, so this is the modified current and time diagram. This is the modified voltage and time diagram. Okay, right, this is the practical curve between voltage and time. This is the practical curve between current and time. Okay, right, so this is breakdown voltage. Okay, so this is spark voltage. Okay, so however the one cycle and on time off time are as usual. Okay, here the spark energy with respect to current and time have been noticed here, right? Right. However, from the figure 2, again let us see the breakdown arises from the acceleration toward the anode of both electrons emitted from the cathode by the applied field and stray electrons present in the gap. Now the second point is these electrons collide with neutral atoms of the dielectric, thereby creating positive ions and further electrons, okay, which in turn are accelerated respectively toward the cathode and anode. Okay, right. So here positive ions and negative ions will be noticed here. Okay, so both anode and cathode. Here cathode is the tool, that is negative electrode, and anode is the workpiece, that is positive electrode. Okay, so however these two are separated by the dielectric fluid. Okay, right. Right. When the electrons and the positive ions reach the anode and cathode, they give up their kinetic energy in the form of heat. Okay, so here thermal energy will be converted into high kinetic energy in the form of heat. Okay, so here temperature of about 8000 to 12,000 degrees centigrade and heat fluxes up to 1017 watts per square meter or attain. With a very short duration, spark of typically between zero point 0.1 to 2000 microseconds, the temperature of the electrodes can be raised locally to more than their normal boiling points. Okay, so in very fraction of seconds, the temperature will be raised up to 8000 to 12,000 degree centigrade. Okay, so because of this high temperature, the material will melts and evaporates. Okay, right. Now let us see the evaporation and all these things here on this figure. Owing to the evaporation of dielectric, the pressure on the plasma channel rises rapidly to values as high as 200 atmospheres. Such great pressures prevent the evaporation of the superheated metal. Okay, right. See, observe this electrode discharge machining spark description. Okay, see here, this is tool wear. Okay, so this is workpiece and this is heat affected zone. Okay, so here the crater that you can see. Okay, and here the liquid metal will form. Here the solidified metal can be seen. and between this the dielectric fluid medium will circulate. So here at the ends the vaporization can be seen. Okay, these are the plasma channels. Here you can see plus and minus. Okay, so here minus is attracting towards workpiece, and the plus, that is positive ions, will attract towards the tool, that is negative electrode. Okay, so however this is recast layer, the bottom of the crater is said to be recast layer. Okay, right. At the end of the pulse, the pressure drops suddenly and the superheated metal evaporates explosively. Okay, metal is thus removed from the electrodes. Okay, as shown in this figure. Okay, so here at the end of the pulse, the pressure drops suddenly and the superheated metal evaporates explosively. Okay, this is important from this figure. Right. Fresh dielectric fluid rushes in. Okay, so it is constantly circulating the dielectric fluid between the tool and the workpiece. Okay, so fresh dielectric fluid rushes in, flushing the debris away and quenching the surface of the workpiece. Right, here this is called, this is an unexpelled. Okay, the unexpelled molten metal solidifies to form what is known as the recast layer. Okay, the expelled metal solidifies into tiny spheres dispersed in the dielectric liquid along with beads on the electrode. The remaining vapor rises to the surface. Okay, what is recast layer? The unexpelled molten metal solidifies to form known as recast layer. Okay, see this figure. This is called recast layer. Okay, the unexpelled molten metal solidifies to form what is known as recast layer. Right. Without a sufficient of time, debris would collect, making the spark unstable. Okay. Next one. This situation creates an arc which damages the electrode and the workpiece. The relation between the amount of material removed from the anode and the cathode depends on the respective contribution of electrons and positive ions to the total current flow. Okay, so here the amount of material removal from the tool and the workpiece or cathode and anode depends on the respective contributions of the electrons and positive ions to the total current flow. Okay, right. The electron current predominates in the early stages of the discharge. Okay, next, since the positive ions are roughly 10 power 4 times more massive than electrons, they are less easily mobilized than the electrons. So here there are two important terms. One is ion, another one is electron. See here, the positive ions are roughly 10 power 4 times more massive than electrons. Okay, they are less easily mobilized than the electrons. Okay, so that is the power of ions. Okay, right. Consequently, the erosion of the anode workpiece should be greater than that of the cathode. Okay, at the end of the EDM action, the plasma channel increases in width and the current density across the inter-electrode gap decreases. Okay, let us see here at the end of the electrode discharge machining action, the plasma channel increases in width and the current density across inter-electrode gap decreases. Okay, right. With the fraction of the current due to the electrons diminishing, the contributions from the positive ions rise and proportionally more metal is then eroded from the cathode. Okay, here cathode means workpiece. Okay, when the fraction of the current due to electrons diminishing, the contributions from the positive ions rise and proportionally more metal is then eroded from the cathode. Right. The high frequency of voltage pulses supplied together with the forward servo control tool motion toward the workpiece enables sparking to be achieved along the entire length of the electrodes. Okay, so here servo control tool motion is the mechanism behind the feeding of the cathode or tool towards the workpiece. Right, again from 5 already we have seen, okay, the voltage and current waveforms during electrode discharge machining. Okay, so these voltage time and current time diagrams regarding breakdown voltage, spark voltage and ionization, okay, and ignition delay, okay, spark energy, that we have all seen. Okay, peak current, average current. Okay, so figure 5 shows all these parameters including cycle on time and off time and spark energy region. Okay, already we have discussed these parameters, right? Next, figure 7 shows the periodic discharges occurring when using an RC generator in EDM. What is RC? Relaxation circuit. Already we have discussed. RC means relaxation circuit generator. Okay, right, here voltage time and current time in periodic discharges in RC type generators. Okay, right, here useful erosion time. Okay, this one, this is discharge time. Okay, so this is charging time. Okay, in voltage and time. Okay, right. So this is a practical periodic discharge diagram. The frequency of discharges or sparks usually varies between 500 and 5 lakh sparks per second. Okay, per second, not in minute. Okay, 500 to 5 lakh sparks will occur in 1 second. Okay, that is the frequency of discharge or sparks. With such high sparking frequencies, the combined effects of individual sparks provide a substantial material removal rate. Okay, see, just imagine in 1 second 500 to 5 lakh sparks, nothing but strikings. Okay, so obviously the material of the workpiece will be subjected to high thermal stress, and at the same time the material will also vaporize, that is leading to material removal, right? The position of the tool electrode is controlled by the servo mechanism, which maintains a constant gap width 200 to 500 microns between the electrode in order to increase the machining efficiency through active discharges. Okay, see here, when the material is constantly subjected to material removal, the gap between the tool and electrode will increase. Okay, so when the material is decreasing, the gap between the tool and the workpiece will increase. Okay, in order to maintain the same gap, a servo control mechanism is adopted, okay, to feed the tool towards the workpiece. Okay, so however, the workpiece will be moved in X, Y and Z directions for the machining of contour shapes. Okay, here the tool will move down. Okay, no lateral directions. Okay, but the workpiece which is fixed on the fixer and mounted on the table will move towards X, Y and Z directions. Okay, right. Okay, these are the references. In the coming lecture, we will see the other mechanisms of the material removal in detail. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.